Hello again, everyone. In this video, I'm going to be discussing transformations of the parent function. Now, the parent function is y equals x squared, and we call it the parent function because it's sort of the most basic version of a parabola that everything else can come from based on changing different values. So we're going to go off of y equals x squared, and we're going to review the concave up or concave down. As a reminder, the concave up are those U-shaped graphs, and concave down will be facing the opposite direction. So the parent function itself is concave up. Basically, if a, the Lie coefficient, is greater than 0, it'll go up. If it is less than 0, it'll go down. So we've done that before, but I wanted to review that before we got to everything else. When we talk about shifting up, shifting down, shifting left, shifting right, we're talking about the vertex itself. So where do we move the vertex? The parent function has the vertex of the origin, but let's say, for instance, we added a 7 at the end outside of the parentheses. We would take that vertex and shift that vertex up 7 spaces. I'm going to make another video going over how this looks on Desmos. But for right now, I just want you to know that this starts at the origin, and this would be 7 spaces above that. Likewise, if we shifted down, if you subtracted 7 after the x squared. Now, looking at the next section here, the shifting left and right, this is the most challenging for people because while it's pretty easy to see that these terms are in parentheses and these are not, a lot of students will tend to believe that a +3 inside of the parentheses would shift the graph right. However, it does not do that. It shifts it to the left. And the reason that is because when you're looking at these nodes here, you want to remember that the vertex is where it changes direction, which is where this squared term needs to be 0. So in other words, you can almost in your head set x plus 3 equal to 0, which would mean that x has to be -3, and -3 is 3 spaces to the left of 0. Likewise, if you look at x minus 3, and you set x minus 3 equal to 0, that would mean x itself has to be 3, and the number 3 is 3 spaces to the right of 0. So you can try this out in Desmos. I'll make a video in a moment just displaying how this works on Desmos, but really keep in mind the changes here, the left and right, and how they relate to the function. This is the part that people have the most difficulty with. Now, stretching vertically versus horizontally. A lot of times students will call vertical graphs, or graphs that are stretched vertically, they'll call them skinnier graphs, and they'll call the horizontal graphs wider graphs. It's important to get the knowledge down and the vocab down on this, though. This is a stretched vertically graph, or a graph that's been stretched vertically, and this one is a graph that's been stretched horizontally. What causes that are the a values. So an a value that's between -1 and 1, so I'll start with that one. Between -1 and 1 is going to be stretched horizontally by whatever factor is there. If we make the a value negative, remember from the beginning here, it just shifts the way that it faces. So in other words, we're just going to turn the graph upside down by making it negative. But it's the other number that we're focused on when we're talking about stretching horizontally or vertically. The 1/2. Even if we made that a -1/2, it would still be a horizontal stretch. It would just be facing the opposite direction. Likewise, if the a value is above +1 or less than -1, that would be a vertical stretch. So in this case, we have +2. But if I made that a -2, it would just be a vertically stretched graph going the opposite direction. So again, making those a values negative wouldn't change whether or not they're stretched vertically or horizontally, but it would change going back up here whether or not they're concave up or concave down.